Welcome back. So, in the last lecture, we were discussing about the idea of Fejér, which essentially is going to answer the question that if we had been given with f hat Fourier coefficient, can we reconstruct the function f? And also we wanted to know if the Fourier series converges, is it going to converge to f or not. So, the first let us try to see the idea of Fejér, which tells us how to get f by knowing f hat. So, as we discussed that basically Fejér asked that even if the sequence S and F, the partial sum of Fourier series may converge or may not converge, what can we say about the Cesaro summability of the Fourier series? In other words, what he asked the following. Now, you consider the Cesaro sum to be S 0 f of x plus up to S n minus 1 f of x, and then this is the average of these n sums. Now, we can, if whether sigma n f converges, that is the question what has been answered by Fejér. So, as we know that a series may not converge, but it can be Cesaro summable. So, this is a genuine question to ask. Now, if we write down the Cesaro sum, this is equal to, now S 0 we know that this is f convolution of d 0, which is the Dirichlet kernel, up to f convolution of d n minus of 1 of x, the average over n, and which we know the linearity of the convolution property, that we can write this as summation n 1 over n equal to 0 to n minus of 1 d n convolution of this. Now, let us denote f n, this is equal to 1 by n summation over n equal to 0 to n minus 1 d n. This is called the Fejér kernel. So, which means in order to see that whether Fourier series is Cesaro summable, we need to check that whether f convolution with Fejér kernel f n, it converges as n goes to infinity. Let us have a closer look at this f n. So, f n of x, this is equal to 1 by n. Now, d 0 is 1, d 1 is e to the power minus of I x plus 1 plus e to the power I x, d 2 is e to the power minus 2 I x plus e to the power minus of I x plus 1 plus e to the power I x plus e to the power 2 I x. It goes on like this, and then e to the power minus I n minus of 1 x plus 1 plus e to the power I x up to e to the power I n minus of 1 x. Okay. So, now there is How many ones are there? There will be n ones. So, this is n. How many e to the power minus of I x will be there? N minus 1, and e to the power I x number is also n minus 1. So, this is n minus 1 times e to the power minus of I x plus e to the power I x. Similarly, there will be how many e to the power 2 I x would be there? N minus 2 e to the power minus 2 I x is n minus 2. So, this is n minus 2 e to the power minus 2 I x plus e to the power 2 I x, and there will be only one e to the power minus of I n minus of 1 x plus e to the power I n minus of 1 x. So, if I take n inside, so this I am going to get 1 plus 1 minus 1 by n e to the power minus of I x plus e to the power I x plus 1 minus 2 by n e to the power minus 2 I x plus e to the power 2 I x, and plus 1 minus n minus of 1 by n e to the power minus I n minus 1 x plus e to the power I n minus of 1 x. Now, if we want to write this in the form of the sum, which is minus of n minus 1 to n minus 1, then 1 minus, as you can notice that if my j is minus 1, then I am also here getting 1 minus 1 by n, and j is plus 1, then I am getting 1 minus 1 by n. Similarly, like this. So, I can write this divided by n e to the power I j x. As you can see that if j is either plus 1 or minus 1, then 1 minus mod j by n is 1 minus 1 is 0. So, safely we can also write this as minus n to n 1 minus mod j by n e to the power I j x. Okay. So, now what are the conditions this Fejér kernel satisfy? Clearly 1 by 2 pi minus pi to pi f n x dx, this is equal to 1 by 2 pi minus pi to pi summation over mod j lesser equal to n 1 minus mod j by n e to the power I j x dx. Now, this is a finite sum. So, we can pull this sum out of the integral, then this is going to be mod j lesser equal to n 1 minus mod j by n, then 1 by 2 pi minus pi to pi e to the power I j x dx. We know that this integral is going to survive only when j is equal to 0 and is equal to 0. This is a j not equal to 0, this is going to be 0. Therefore, for j equal to 0, this is 2 pi gets cancelled. So, what we get is that this is equal to 1. This also exactly, this is Dirichlet kernel also satisfies this. The problem in the Dirichlet kernel, what we had observed is that when we are discussing about minus pi to pi mod of d n x dx, this we have seen that this goes to infinity as n goes to infinity. That means, we do not have the control of the Dirichlet kernel when we are taking the modulus. That means, the oscillation is making Dirichlet kernel integral to be 1, but when we put the modulus, we are killing that kind of cancellation. So, now this cancellation is going to blow up. That is why we saw that we do not have the control over modulus integral of the modulus of Dirichlet kernel. Now, are we in a position where we can say that the Fejér kernel behaves better than that of the Dirichlet kernel vis-a-vis if we take the modulus inside the integral. So, before that, let us look at this identity, this lemma. This says that f n x has a form which is equal to 1 by n sin square n by 2 x divided by sin square x by 2. That means, f n, if x is not equal to 0, f n is a non-negative quantity. Therefore, if we can get this, assuming this lemma, then modulus of f n is equal to f n. F n is a non-negative quantity. Therefore, we are going to have the bound of modulus of f n as independent of n. What is the proof of this equality? Now, n times f n of x, let us write it down. This is equal to n equal to 0 to n minus of 1. This is nothing but d n of x. That is what is our f n by definition. Now, this is equal to summation from n equal to 0 to n minus 1 sin n plus 1/2 of x by sin x by 2. That is what the definition of Dirichlet kernel is. Therefore, if I multiply and divide by sin x by 2, I will take out, and then if I do a sin square x by 2, what I have got inside the sum is 2 times sin n plus 1/2 of x sin x by 2. Now, this is in the form of 2 sin A into sin B. So, we are familiar with the trigonometric identity. This is going to be, this is cos A minus B minus cos A plus B. So, this is cos A minus B is n x minus cos n plus 1 of x. Now, this is a telescopic sum. Therefore, only the first and the last term is going to survive. Therefore, this is 2 by 1 by 2 sin square x by 2. This cos 0 is 1 minus cos n x, n minus of 1 plus 1 is n. Now, cos 0 is 1. So, this is 1 minus cos n x. So, 1 minus cos x is equal to 2 sin square x by 2. So, we get 2 sin square x by 2 into 2 sine square n by 2 of x. This is equal to the required identity what we wanted to get, and this is for x not equal to 0 and x is in minus pi to pi, x not equal to 0. So, there is no other point where sine square x by 2 is going to be 0 except at x equal to 0, because x by 2 is going to lie in minus pi by 2 to pi by 2. So, that is good. So, as a corollary what we get is that 1 by 2 pi minus pi to pi mod f n x dx is equal to 1 by 2 pi minus pi to pi f n x dx, because it is a non-negative quantity and which we have seen that this is equal to 1. So, this is a big advantage over the Dirichlet kernel, where we did not have control over the integration of the modulus of d n. Good. So, now what happened when x goes to 0? We now know that f n of x for x not equal to 0 is sine square n by 2 x by sine square x by 2, which I will divide and multiply by this is 1 over n sine square n by 2 x by n square by 4 x square into n square by 4 x square, and then x square by 4 by sine square x by 2 into 1 over x square by 4. Now, this goes to 1, this also goes to 1, this x square by 4 x square 1 over x square by 4 get cancelled, and so 1 by n into n square. So, this goes to n. So, at 0 this Fejér kernel is picking up and is taking the value n. So, let us try to sketch this. Suppose if you take n equal to 2. Now, let us figure out where f n x is going to be 0. So, that means n by n is 2, therefore, x is going to be 0 means x is equal to pi. So, that sine pi or minus pi is 0. So, this is an even function. Now, if n equal to 3, then 3 by 2 of x is equal to n pi. Therefore, what is the corresponding n which is going to have? Only one n, because x is between minus pi to pi. So, therefore, x is equal to 2 pi by 3. This is 2 pi by 3, and it is an even function. So, this is minus 2 pi by 3, and here it is taking the value n equal to 3 is here. So, on this side if we do, this is 0 and then this is writing like this. Suppose now if I take n is equal to 5, then this is 5 by 2 x, this is equal to n pi. Therefore, how many n equal to 1 is going to be there, n equal to 2 is going to be there. Therefore, x is equal to 2 pi by 5 and 4 pi by 5. So, here it is 4 pi by 5 and then this is 2 pi by 5 and n equal to 5 is here. So, now this is going to look like, this is going to drop here and then this, and because this is a even function, this is 2 pi by 5, this is minus 4 pi by 5. So, this is how this is going. So, similarly, if we are taking a large n, then this is something which is going to be there will be more and more zeros. So, this will somehow this is going to be look like this, and which is a one periodic function. So, now closer and closer we come to, if we take n large, then we will have more number of 0, and this is going to be oscillate with lot of zeros, and it is going to pick up at 0, which is going to take the value n. Now, let us come to the theorem of Fejér, what Fejér said, which is one of the very important result in for this course, and which has many application. So, it says that let f be a Riemann 2 pi periodic Riemann integrable function on minus pi to pi. If f is continuous at x naught, then f convolution with f n at x naught, this converges to f of x naught as n goes to infinity. And if f is continuous throughout, or rather on minus pi to pi, then f convolution of f and x converges to f of x uniformly. So, before proving this theorem, let us have a close look at another important feature of Fejér kernel. This I will put it as a lemma. Let delta positive, if mod x is greater than delta, then limit n goes to infinity f n of x, this is equal to 0. So, how do we prove this? Now, you see, mod x is greater than delta. Therefore, if I look at the curve of sin x by 2, then this is going to be, the curve is on the positive axis, this is going to be this. So, this x by 2, this is pi by pi, this is 2 pi. So, 0 to, so at the, so now suppose delta is somewhere here, then sin is greater than sin delta by 2. Similarly, the modulus is here. Now, mod greater than delta means this is sin delta by 2. We can write this as therefore, sin square is greater than sin square delta by 2. Therefore, f n of x, this is lesser equal to 1 by n sin square n by 2 x into 1 by sin square delta by 2. Now, for each delta is fixed. Now, this is lesser equal to 1 by n, because sin is always bounded by 1. So, this is 1 by sin square delta by 2, and which goes to 0 as n goes to infinity. So, now what it happens that if I am going away from the origin, the area which is covered by the Fejér kernel for large and large n. So, if the Fejér kernel is going to look like something like this. Now, if I am going for large n, this is again it is going to be, this distance would be very small. Now, it will go like this. So, therefore, the area under this curve away from the 0, this is going to be negligible for large n, and that is what we are going to exploit in order to get the result what Fejér's theorem. So, now proof of the theorem. So, we know that f is continuous at x naught. Therefore, for epsilon positive, there exists a delta greater than 0 such that mod of f of x naught minus of y minus of f of x naught, this is less than epsilon by 2 whenever mod y is less than delta. Then x naught minus this is going. Now, the second thing is that take this delta, take delta and epsilon as above, because you start with a epsilon, then you are getting a delta by the continuity, and for that delta from the lemma there exists a n sub naught such that limit n goes to so rather I will put it integral of mod y greater than delta mod of f n of y dy is less than epsilon by 2 into this, where f is, this is our notation, supremum over x mod of f of x for all n greater or equal to n sub naught. Okay. Now, what we are interested in mod of f convolution with f n at x naught minus f of x naught. This by definition is 1 by 2 pi minus of f of x naught. Now, here on there are two quantities, one side is integral, then the other side there is no integral. So, what we would like to do is that because we know the integral of f n x is equal to 1, therefore, this is minus pi to pi f of x naught minus of y f n of y dy minus f of x naught to minus pi to pi f n y dy. Now, this is less or equal to 1 by 2 pi minus pi to pi mod of f of x naught minus of y minus of f of x naught and mod of f n, and f n is a non-negative quantity. So, this is less than this. Now, what we do is that 1 by 2 pi. Now, we will break the integral into small y near origin and 1 by 2 pi integral away from the origin. This is mod of f of x naught minus of y. Okay, so, we will continue with this by our previous observation that how we are going to make this quantity small in the next lecture. Thank you.